So we will be talking on electric potential. Now this is about energy associated with electrical interactions. Now every time we turn on a light, listen to an MP3 player, or talk on a mobile phone, now we are using electrical energy. So, when a charged particle moves in an electric field, now the field exerts a force that can do work on the particle. Now, this work can always be expressed in terms of electric potential energy. Now, we will be describing electric potential energy using a new concept called the electric potential. Now, in this discussion, we'll be needing the concepts of potential and voltage. So let us review these three essential points. So first is that when a force acts on a particle that moves from point A to point B, now the work done by the force is given by a line integral. So the work done by the force from point A to point B is equal to the integral from point A to point B, force times dl, and we got the integral from point A to point B, force cosine phi dl. So dl here and here are the infinitesimal displacement along the particle's path, and our phi is the angle between our force and our dl at each point along the path. Now second is that our force is conservative. So the work done by a force can be expressed in terms of potential energy. So when a particle moves from a point where our potential energy is at point A to a point where our potential energy is at point B, so we have the change in potential energy equal to the potential energy at point B minus the potential energy at point A. And that is also equal to the negative of our potential at point B minus the potential energy at point A. And we got the negative change of our potential energy. And then this will be our work done if our force is conservative. Now third is that we have the work energy theorem. So our delta K, or the change in our kinetic energy, is equal to the kinetic energy at point B minus the kinetic energy at point A. So if only conservative forces do work, so our equation, the negative change of our potential energy, will give us the total work. So we have to equate work energy theorem and the negative change of our potential energy. So we got the kinetic energy at point B minus the kinetic energy at point A equals to the negative change of our potential energy. And this will give us the kinetic energy at point A plus the potential energy at point A equal to the kinetic energy at point B plus the potential energy at point B. So this will be our total mechanical, kinetic plus potential theorem. Now on electric potential energy in a uniform electric field. So we have here a pair of parallel metal plates that sets up a uniform electric field with magnitude E. Now our electric field exerts a downward force which is equal to Q naught E. On the positive charge Q naught. So the charge moves downward, this charge moves downward with a distance d. So we have a distance d. So meaning to say it is from point A to point B. Now the force of the test charge is constant and independent of its location. So our work done from point A to point B is equal to our force times our displacement. So since we have a force equal to Q naught E, so our work done from point A to point B is equal to Q naught E D. So this is the product of the force magnitude and the component of the displacement, which is downward direction of the force. So our work is positive since the direction of our Q naught or our charge in our electric field is just the same. So our y component of our electric force is the negative of our Q naught E, and this is constant. So we have no x and y, we have no x and z components since our charge is only moving in the y component. These are the conditions under electric potential in a uniform electric field. So in A, we have positive charge that moves in the opposite direction of our electric field. And in B, our positive charge moves in the direction of our electric field. So we say that we have a pair of parallel metal plates that sets up a uniform electric field with magnitude E. So the electric field exerts a downward force Q naught E. So the positive, that is on the positive charge Q naught. So in A, our charge is moving upward and our electric field is moving downward. So what happens is that our field does negative work on the charge, and then our potential energy increases. Now in B, our charge, since it is moving along with the direction of our electric field, then our electric field is doing a positive work on the charge, and then our potential energy decreases. So these are the conditions for negative charge, and this is under the concept of electric potential energy in a uniform electric field. Now for A, we have our negative charge moves in the direction of our electric field, and in B, we have our negative charge moving in the opposite direction of our electric field. So we say that we have a pair of parallel metal plates that sets up a uniform electric field with some magnitude E. So our electric field exerts a downward force which is equal to Q naught E, and that is on the negative charge Q naught. So when our negative charge move in the direction of our electric field, so it is moving along with the direction of our electric field, so the field does negative work on the negative charge, and then our potential energy increases. Now for the negative charge that moves opposite the direction of our electric field, now our field does a positive work on the negative charge, but then our potential energy decreases. Now for gravitational force, equal to the negative product of our mass and our acceleration due to gravity. So we have a potential equal to the product of our mass, acceleration due to gravity, which is equal to 9.8 meter per second square, and we have some height y. Now for electric force, which is equal to the negative Q naught E, so we have a potential Q naught E at some point y. So when a test charge moves from height at some height ya to some height yb, so the work done on the charge by the field is, so we'll be using the equation for when force is conservative. So the work done by force from point A to point B is equal to the negative change in our potential energy. So that is equal to the negative of our potential energy at point B minus the potential energy at point A. So we substitute the value of our potential energy in for our electric force. So we got Q naught, negative Q naught E y at some point B minus the Q naught E y at some point A. So we got, for our work done on the charge by the field, so we have Q naught E y at point A, at some point A, minus our height at some point B. So this is our work done on the charge by the field. Now we are on electric potential energy of 2-point charges. So considering this illustration, now say we have a test charge Q naught that moves along a straight line extending radially from a charge Q. Now as it moves from point A to point B, now the distance varies from our R sub A and our R sub B. So the force on Q naught is given by the Coulomb's law and its radial component. So it is equal to 1 over 4 pi epsilon naught Q naught over R squared. Now if our Q and Q naught have same signs, either positive or negative, then our force is repulsive. But then if our Q and Q naught have negative signs, so our force now is attractive. So force is not constant during the displacement. So we integrate in order to calculate the work done on Q naught by this force as Q naught moves from point A to point B. So the work done on Q naught from point A to point B is equal to the integral from R sub A to R sub B, or force dr. This is equal to the integral from R sub A to R sub B, 1 over 4 pi epsilon naught Q naught over R squared dr. And then we got Q naught over 4 pi epsilon naught we have 1 over r sub a minus 1 over r sub b. So the work done by the electric force for this particular path depends only in the endpoints. So considering a more general displacement where A and B do not lie on the same radial line, so the work done on Q naught during the displacement is given by line integral from point r sub A to point r sub B, force cosine phi dl, and it gives us integral from point r sub A to point r sub B, 1 over 4 pi epsilon naught q naught over r squared cosine phi dl. So again, this is the work done on Q naught during the displacement. So the work done on Q naught, the charge Q naught, by the electric field charge Q does not depend on the path taken but only on the distance r sub A and r sub B. So again, our test charge Q naught is moving. Now in this illustration, it moves from point A to point B along an arbitrary path. Now our illustration shows that our cosine phi dl is just equal to our dr. So our work done depends only on the change of dr in the distance r between charges, which is the radial component of the displacement. So the work done on Q naught, E again, is produced by Q, depends on the r sub A and r sub B, not on the details of the path. So if our Q naught returns to its starting point by a different path, so the total work done in the round trip displacement is 0. So all of those things that I have said are the needed characteristics for a conservative force. So thus the force on Q naught is a conservative force. So if our Q naught is a distance r sub A from Q, from our charge Q, so we can define the potential energy to be potential energy at point A equal to Q naught over 4 pi epsilon naught r sub A. But when our Q naught is a distance r sub B from our Q, now we can define the potential energy to be potential energy at point B equal to q naught over 4 pi epsilon naught r at point B. So the potential energy when the test charge q naught is at any distance r from charge q is equal to 1 over 4 pi epsilon naught q naught over r. So this is again our electric potential energy of 2-point charges q and q naught. Now these are the graphs of potential energy of 2-point charges versus their separation r. So in A, we have our q and q naught have the same sign, so they are either both positive or both negative. So in this graph, our potential energy is greater than 0, and as r approaches to 0, our potential energy approaches to positive infinity, and when our r approaches to infinity, our potential energy approaches to 0. Now in B, our charge q naught and q have opposite signs, so our potential energy is less than 0, and then as our r approaches to 0, our potential energy approaches to negative infinity, and then as our r approaches to infinity, our potential energy approaches to 0. We are now on electric potential energy with several point charges. So suppose that our electric field in which our charge q naught moves is caused by several point charges. So say we have 3 charges. We have q1, q2, and q3 at distances r1. So say this is our q naught. So from q naught to our q1, we have a distance r1, and from our q naught to our q2, we have a distance r2, and from our q naught to our q3, we have a distance r3. So the total electric field at each point is the vector sum of the fields due to the individual charges, and the total work done on our charge q naught during any of this displacement is the sum of the contributions from the individual charges. So from the equation for electric potential energy of 2-point charges q and q naught, which is equal to 1 over 4 pi epsilon naught q naught over r, So from this equation, we can conclude that the potential energy associated with the test charge Q naught at point A, so this will be our point A, is the algebraic sum and not a vector sum. So now our equation for a point charge Q naught and collection of charges is that we have equal to Q naught over 4 pi epsilon naught Q1 over R1 plus Q2 over R2 plus Q3 over R3, or this can be written as Q naught over 4 pi epsilon naught summation of our I Q sub I over our R sub I. So this is our equation for a point charge Q naught and its collection of charges Q sub I. So when our Q naught is at a different point B, so the potential energy is given by the same expression, but our distances R1, R2 are again the distances from Q1 and Q2 until it reaches to point B. So the work done on a charge Q naught when it moves from A to B along any path is equal to the difference of our potential energy at point A and the potential energy at point B. That is between the potential energies when Q naught is at point A and point B. So now we can represent any charge distribution as a collection of point charges. So our equation for a point charge Q naught and charges and collection of charges Q sub I, so this equation, it shows that we can always find a potential energy function for any static electric field. Now it follows that for every electric field due to a static charge distribution, the force exerted by that field is conservative. Now this equation gives the potential energy associated with the presence of a test charge Q naught and the electric field that was produced by our charges Q1, Q2, and Q3. But there is also potential energy involved in assembling these charges. Now, if we start with charges Q1, Q2, and Q3, which are all separated from each other by an infinite distance, and then bring them together between the Q sub I and Q sub J is a distance Rij, and the total potential energy is the sum of the potential energies of interactions for each pair of charges. So we have or we can write this as potential energy equal to 1 over 4 pi epsilon naught summation of our I must be less than, with the value of our j, q sub I and q sub j over our distance r I j. So this sum extends over all pairs of charges. Now, we do not let our I, the value of I, be equal to the value of our j, and that is because that would be an interaction of charge with itself, and we only include terms with I is less than j to make sure that we count each pair only once. So, electric potential. Electric potential is the electric potential energy per unit charge, and we define potential at any point in an electric field as the potential energy per unit charge associated with a test charge Q naught at that point. So, from this equation, we can get another equation for our potential energy. So, we have potential energy equal to Q naught V. Since our potential energy and charge are both scalars, so our potential is now scalar. So from the owner of the Italian electrical experimento Alessandro Volta, the SI unit of potential is called 1 volt. So 1 volt is equal to 1 joule per coulomb. So let's put this equation, which equates the work done by the electric force during a displacement from A to B to the quantity of our negative change in potential energy. And we got the negative of our potential energy at point B minus the potential energy at point A. So on a work per unit charge basis, we divide the equation by Q naught, obtaining so as you can see, the potential energy at point B divided by or over our Q naught is just our potential. Same goes to our potential energy at point A divided by the charge Q naught. So we get negative of the potential at point B minus the potential at point A. This is just equal to potential at point A minus the potential at point B. So the work done per unit charge by the electric force when a charged body moves from point A to point B is equal to the potential at A minus the potential at point B. So we have an instrument that measures the difference of potential between 2 points, and that instrument is called voltmeter. We are now on calculating electric potential. Now to find the potential due to a single point charge Q, we divide this equation for electric potential energy of 2-point charges Q and Q naught by our Q naught. So by dividing this equation by Q naught, so we got uh, since our potential is equal to our potential energy per unit charge, so we have 1 over 4 pi epsilon naught q naught over r divided by q naught. So our q naught here and here will be cancelled, and we got 1 over 4 pi epsilon naught q over r. So this will be our equation for potential due to a point charge, where our r is the distance from the point charge q to the point at which the potential is evaluated. If we have a positive charge, then the potential that it produces is positive at all points. But when we have a negative charge, then the potential that our charge produces is negative everywhere. So in order for us to get an equation for potential due to a collection of point charge, so we need to use the equation for point charge q naught and collection of point charges q sub I. So remember that our potential energy is equal to q naught over 4 pi epsilon naught summation of q sub I over r sub I. Now this is our equation for point charge q naught and collection of point charges q sub I. So by dividing this by q naught, so q naught will be cancelled. So we now got 1 over 4 pi epsilon naught q sub I over r sub I. So this is our equation for potential due to a collection of point charge, where our r sub I is the distance from the ith charge and our q sub I is the point at which our potential is evaluated. So just as the electric field due to a collection of point charges is the vector sum of the field produced by each charge, now the electric potential due to a collection of point charges is the scalar sum of the potential due to each charge. Now when we have a continuous distribution along the line over a surface or through a volume, we divide the charge into elements dq, and sum in equation for potential due to collection of point charge becomes an integral. So our potential is equal to 1 over 4 pi epsilon naught the integral of dq over r. So this will be our equation for potential due to a continuous distribution of charge, where us go to finding electric potential from electric field. So when we are given a collection of point charges, the equation for potential due to a collection of point charges is the easiest way to calculate the potential V. So again, our equation for potential due to a collection of point charges is 1 over 4 pi epsilon naught Q sub I over R sub I. Now, to calculate the potential energy, again, this is the best or the easiest way. But in some problems in which the electric field is known or can be found easily, it is easier to determine V or potential from electric field. Now, the force on the test charge Q naught can be written as equal to Q naught E. So from equation by the work done by the force equal to integral from point A to B, force times dl, the work done by the force as the test charge moves from point A to our point B is now be given by, since our F is equal to this, so the work done by an electric force is equal to the integral from point A to point B, the value of our force Q naught E times dl. Now, if we divide this equation by Q naught, then we got the integral from point A to point B. The Q naught will be cancelled, so we have the electric field times dl, and this is also equal to integral from point A to point B, E, or our electric field, cosine phi dl. So again, our dl is the infinitesimal displacement along the particle's path, and our phi is the angle between our electric field and our dl. So this equations is our potential difference as an integral of our electric field. Now, if we compare it to our potential at point A, the equation potential at point A minus the potential at point B, so this is the equation that we have obtained after we divide Q naught to the equation for the work done by force from point A to point B, equal to the negative change of our potential energy. Now, the value of our VA minus potential A minus the potential at B, at point B, is independent of the path taken from point A and point B. So, if the result of the integral E dot dl or E times dl is positive, now the electric field does a positive work on the charge or in the positive charge. Now, as it moves from A to B, in this case, the potential energy decreases as the potential energy decreases as the test charge moves. So, the potential energy per unit charge So again, the potential energy per unit charge, this is our V, decreases as well. So we need to say that our potential at point B is less than the potential at point A. So our VA minus VB, our potential at A minus the potential at B, will result as positive. So if you move in the direction of the electric field, potential decreases. Now if you move in the direction opposite to the electric field, then the electric potential increases. So say we have a positive charge and electric field is moving away, or it is directed away from the charge. So as U moves toward the charge, what happens is that your V will increase. But when you move away from the charge, then the opposite thing would happen. So your potential will decrease. Now, again, the electric field is directed away from the charge. So, and we have a potential equal to Q over 4 pi epsilon naught R is a positive at any finite distance from the charge. Now, if you move away from the charge in the direction of the electric field, so you move toward lower values of the potential. Now, if you move toward the charge in the opposite direction of the electric field, then you are moving toward greater values of the potential. But what if you have a negative charge? So and the electric field is directed toward the charge. So as you move toward the charge, the usual thing that would happen is that your potential will decrease, and if you move away from the charge, then the potential will increase. Now, again, if you move toward the charge, you are moving in the direction opposite to the electric field and in the direction of a more decreasing potential. Now, as you move away from the charge, the negative charge, in the direction opposite to the electric field, so you are moving toward increasing or less negative values of the potential. So also, a positive charge Q naught experiences an electric force in the direction of the electric field. Now, toward lower values of the potential, a negative charge experiences a force opposite to the electric field. Now, that is toward higher values of potential. Thus, the positive charge tends to fall from a high potential region to a lower potential region. Now the opposite happens to this illustration, in which our charge is negative. Now let us discuss on electron volts. The magnitude of the electron charge can be used to define a unit of energy that is useful in many calculations with atomic and nuclear systems. When a particle with charge Q moves from a point where the potential is at point B to a point where the potential is at point A, so the change in the potential energy is potential energy at point A minus the potential energy at point B. So, getting back from our previous lessons, our U, or our potential energy, is equal to Q naught V. So, here we got Q naught V A, or potential at point A, minus the potential at point B. So, this will be equal to Q V at point A and point B. So, if the charge Q equals the magnitude of the electron charge, so we have 1.602 times 10 to the negative 19 coulomb, and the potential energy, or the potential difference, is VAB, or the potential energy at point A and B, is equal to 1 volt. So the change in the energy is, by using this equation, so we have 1.602 times 10 to the negative 19 coulomb times the potential energy at point B and A, which is equal to 1 volt, and this will give us 1.6602 times 10 to the negative 19 joules. So this quantity of energy is defined to be the 1 electron volt, which is equal to 1.602 times 10 to the negative 19 joules. Now let us discuss on ionization and corona discharge. Now this is a result from numerous practical consequences. Now it relates to the maximum potential to which a conductor in air can be raised. Now this potential is limited because air molecules become ionized and air becomes a conductor at an electric field magnitude of about 3 times 10 to the 6 volts per meter. Now, if we assume that for a moment Q is positive, so for the electric potential at the surface and field magnitude at the surface of a charge conducting sphere, so we note that our V, or our potential at the surface, equal to the field magnitude at the surface times R. Thus, our EM in which this represents our electric field magnitude, at which air becomes conductive, also known as dielectric strength of the air. Then the maximum potential, so the maximum potential to which a sphere conductor can be raised is equal to R E sub m. So if we have a conducting sphere which has a radius from the air equal to 1 cm, so our maximum potential would be, this would be 10 to the negative 2 meter times the 3 times 10 to the 6 volts per meter. This is the value of our electric field magnitude. So this gives us 30,000 volts. So no amount of charging could raise the potential of a conducting sphere of this size in air higher than 30,000 volts. Now, attempting to raise the potential further by adding extra charge would cause the surrounding air to become ionized and conductive, and the extra added charge would leak into the air. Now let us discuss on equipotential surfaces. Now field lines helps us visualize electric fields. Now potential at various points in an electric field can be represented graphically by equipotential surfaces. Now these use the same fundamental idea as topographic maps, like those used by hikers and mountain climbers. Now, this is what a topographic map looks like. Now, the contour lines are drawn through points that are all at the same elevation. If we have a mass M that were being moved over the terrain along such a contour line, the gravitational potential energy, or the mgy, the product of our mass, acceleration due to gravity, and some height, does not change because the elevation of our y, or our some height, is constant. Now, the contour lines are really curves of constant gravitational potential energy. And also the contour lines are close together where the terrain is steep and there are large changes in elevation over a small horizontal distance. So these contour lines are further apart where the terrain is gently sloping. So allowing a ball, so if you allow a ball to roll downhill it will experience the greatest downhill gravitational force where the contour lines are closer together. So by analogy, these contour lines on a topographic map, an equipotential surface is a three-dimensional surface on which the electric potential is the same at every point. Now, if a test charge Q0 is moved from point to another point on such a surface, now the electric potential energy Q0 V will remain constant. So, we have no points that can be at two different potentials. So, the equipotential surfaces the equipotential surfaces for different potentials can never intersect or touch. So, I have drawn three illustrations. Now, for this illustration, we have a single positive charge, and for this picture, we have an electric dipole, and for the third picture, we have two equal positive charges. So now, the cross section of equipotential surfaces where the blue lines, or this one, and the electric field lines for assemblies of point charges where these lines. Now these are the equal potential differences between adjacent surface. So I have shown three illustrations. So for this first illustration, we have a positive charge. So what happens to our electric field is that it moves away from our charge. Now for the second illustration, we have negative and a positive charge. Now in the negative charge, our electric field lines are moving toward the negative charge, and in our positive charge, the electric fields are moving away from our positive charge. Now for the third illustration, we have an equal to equal positive charges. So we have in this illustration, our electric field lines are moving away from the charge, but then when it comes in here, the electric field lines will never intersect, or it will never touch each other. So now, in general, field lines are curves and equipotentials are curved surfaces. But for the special case of a uniform field in which the field lines are straight, parallel, and equally spaced, the equipotentials are parallel planes perpendicular to the field lines. So the actual equipotential surfaces are three-dimensional at each crossing of an equipotential and a field line. The two are perpendicular. So in these three illustrations, we have drawn equipotentials here, these colored blue curves, so that there are equal potential differences between adjacent surfaces. Now in regions where the magnitude of E is large, the equipotential surfaces are close together because the field does a relatively large amount of work on the test charge and in a relatively small displacement. So this is the case near the point charge in figure 1, in our figure 1, or in between the 2 point charges in our figure 2 here in our illustration. So we note that these regions of field lines are also closer together. So we are now on the potential gradient. Since our electric field and our potential are closely related to each other, so this equation for potential energy as an integral of E, so this will help us to restate and express one aspect of the relationship of the electric field and potential. So we have the potential at point A minus the potential at point B equal to the integral from point A to point B, our electric field times dl. So we know that our dl is the infinitesimal displacement along the particle's path. Now, if we know that our electric field at various points, so we can use this equation to calculate potential differences. In this section, we show how to turn this around. If we know the potential V at various points, we can use it to determine the electric field. So regarding the potential as a function of the coordinates x, y, and z of a point in space, we will show that the components of electric field are related to partial derivatives of V, of our potential V, with respect to x, y, and z. So in this equation, our potential at A minus the potential at B is the potential of A with respect to B, and that is the change of the potential encountered on a trip from B to A. So we can write this as potential at point A minus the potential at point B equal to the integral from point A to point B dV, that is equal to the negative from point A to point B dV, where in here our dV is the infinitesimal change of the potential accompanying an infinitesimal element dl, and that is of the path from B to A. So comparing these two equations, so we have negative the integral from point A to point B dV equal to the integral from point A to point B E, our electric field, that dl. So these two integrals must be equal for any pair of limits A and B. And for this to be true, the integrands must be equal. Thus, for any infinitesimal displacement dl, so we have negative dV equal to our electric potential times dl. And to interpret this expression, we write dl and electric field in terms of their components. So for electric field, we have I hat E sub x plus j hat E sub y plus k hat E sub z. And for dl, we have I dx plus j dy plus k. This is I hat, j hat, and k hat dz. Then we'll be having a negative dv equal to e sub x dx plus e sub y dy plus e sub z dz. Now suppose the displacement is parallel to the x-axis. So our dy is equal to our dz, and this will be equal to 0. So then our negative dv e sub x dx or dx is our e sub x is equal to the negative of our dv over dx, where the subscript reminds us that only x varies in the derivative. So recall that our potential is a general function of our x, y, and z. But this is just what is meant by the partial derivative of v over the partial derivative of x. The y and z components of our electric field are related to the corresponding derivatives of the potential. In the same way, so we now have ex, e sub x equal to the negative of the partial v over partial x, our e sub y equal to the partial of our v over the partial of our y. And for our z component, we have e sub x equal to our partial of v over the partial of z. So this is the components of our electric field in terms of the potential V. So this is consistent with the units of electric field being volts per meter. In terms of units, unit vectors, we can write E as can have electric field equal to the negative of our I hat partial V over partial X plus J hat partial of our V over partial of our Y plus K hat partial of our V over the partial of Z. So this is in terms of, so our electric field is in terms of our potential V. So in the vector notation, the following operations were called the gradient of the function f. So our gradient, the function of f, is equal to our I hat partial over partial of x j plus j hat partial over partial of y plus k hat partial over partial of z times our f. So the operator denoted by the gradient is called grad or del. So thus the vector notation is electric field is equal to the negative of the gradient of our V. So E is the negative of the gradient of V, or we can read this as E, or electric field, equals the negative gradient V, and the quantity gradient V is called the potential gradient.